So good afternoon, everyone. I'm Jasjappan Singh, a BTech fourth year student at Manipal, Jaipur, and this project was done by me and Romir Malik at we are designation interns at NIO under the guidance of Dr. Pramod Maurya. So this will be the structure of the presentation, and I'll be going through this in this order. So first of all, let me start by the structure of a hydroelectric dam. So what happens is we have this dam area and we have a spilling basin through which the water falls down through the gears, and then it contains excess of kinetic energy. So it's necessary to dissipate that excess energy in order to restore the flow of the river. And that entire thing is done by the structure called as the stilling basin. So stilling basin is a corrosion protection structure that dissipates the extra kinetic energy possessed by the water. So it's an outlet erosion control structure. It dissipates the energy and it also restores the river flow to prevent soil erosion. So it also undergoes, excessive corrosion because of high force of water that the water exerts, and it requires maintenance. So currently, the inspection methods involve a human diver that go down and inspect that basin for how reinforced the concrete is, or how well the cracks are forming, or when it needs a repair. So the limitation is, of course, there's a poor visibility for the diver, there's a high cost factor involved, and of course, there's a harsh environment, and of course, there's a margin of errors. So, well, ROVs are an optimal solution to these limitations, and also or can also collect data for further analysis. So, for this specific project, I went with the BlueROV 2, and BlueROV 2 is available at NIO, and so we had a custom raw stack. So, for coming to the methodology, we have this ROV in the stilling basin structure, and the ROV is we are using yellow ropes to mark out the area to be surveyed. So the ROV follows the ropes and it is localizing in the area based on the Aruko markers that it has previously loaded. So what we are basically doing is we are using camera to perceive the environment, using the rope to follow the path, and then we are using control to follow the path, and then we are doing crack detection using the YOLO models. So this is the overall structure of how the project is structured. So first we have the data streaming, the image streaming, and then we do some image enhancement to enhance the yellow features of the rope, and then we do the perspective transform, then we generate the segmentation mask, and then we're using a sliding window based approach to follow the path. Then we're doing the path estimation for both the sway and yaw of the vehicle. So to implement this project, we are using ROS and Gazebo. ROS is a robot operating system. It's one of the industry standards right now, and we're using Gazebo for simulation, which helps us make the environments in virtual worlds. So for coming to image enhancement, we're using contrast limited adaptive histogram equalization. This is just a comparison of what's going on. This is a screenshot from the Gazebo simulator. And here it is after we have done the HSV and Clay equalization. So Clay is an advanced form of histogram equalization. It basically divides by default into 8x8 pixels, and then we do histogram equalization on those grids. And yeah, this is just a comparison of how the results are magnified. So in HSV field, we can also see the rope is clearly visible, which might not be true in the RGB color field. So coming to segmentation, the first approach to segment the rope to follow it was going for deep learning approach, but one of the limitations is the number of parameters. A mobile net based model or a basic model even has around 13 million parameters, and that's just for the encoder part. Decoder has more. So well, deep learning was not suited because of the limitations of onboard memory of the ROV, and that is why we chose to go for the conventional methods, which is the HSV based segmentation methods. So these are the equations for HSV segmentation methods. We have defined the ranges for HSV values of the rope, and once it is detected, it segments into 0 and 1 values. So this is a screenshot from the Gazebo simulation that's going on. So here is the blue arrow, and it has a camera view. So it's seeing the rope, and based on that, it's drawing the sliding windows on this rope after segmenting it. So the next part is the sliding window algorithm. So what we are doing is we are first of all taking the image from the ROV, we are applying Clay equalization, and then doing a HSV transform. What we then get is this kind of an image. Then we are doing a perspective transform so that we can remove the excess noise and the excess of the data, which might not be relevant for our detection tasks. And then I do the segmentation to generate this white line, and then I do the sliding window algorithm. So why the sliding window? Well, first of all, we initially tried with just segmenting the rope and using its centroid to position the ROV. One of the main issues is the rope might not be segmented properly due to some background noises or some yellow objects or other objects that might be present in the area. So what sliding window helps is it provides the centroids of all these windows, and that can help actually fit a curve to the rope and determine the rope even for curved ropes. So for path following, we're using a pure pursuit or a carrot based controller. So what we have now is a rope, and we have a window that describes, the structure of the rope. We have the centroids of all the points lying on it. And now what I effectively need to do is follow the rope. So our method for this was we took the first sliding window. This blue box you can see is the first sliding window of the rope detected. And I have the centroid values that is returned by the function. So what I actually need to do to center the ROV on the rope is basically move this blue sliding window towards the vehicle position. In order to do that, what we're using is a donkey carrot approach, what I call. So we have a carrot and the donkey is following. That's what, in simpler terms, we are doing. We're calculating the angle, how much oriented it is, the carrot, and we're taking a distance d forward, because we can't just move right. It's better to move forward to merge with the path that's to be followed. And we also have this error which cannot be corrected by only shifting the yaw. So we're also calculating the yaw error. So what we are doing is using this function to calculate the tan inverse, and it comes in the range of minus pi to pi. So we are then limiting the values on the range of 90 to 90, because in case of a noise, it may take some steep turn. So we're doing that to limit the values. So what we eventually have is a correction angle, and then we're also calculating the sway error, which essentially is this distance. So we have this theta angle that needs to be corrected. That means the ROV is to be rotated this way. And we also have this E value, which means how much the ROV needs to shift to center itself across the first sliding window. The idea here is basically, if at every frame, if the ROV is able to center itself across the first window, it will be able to center itself eventually as it moves on. So that's how we are doing it. And of course, this also falls true in case of curved paths. So this method we are using to calculate both the errors, and then we're using a k variable to limit the extent at which the values are being applied. These theta angle and the sway angle are being applied, and we're using getting the orientation of the current heading of the ROV, and we're adding it to the k theta value. So based on that, we have the control of the ROV to follow the rope. The next part is concrete crack detection. For detecting concrete cracks on board, we're using this model called as YOLO V7. So YOLO is a single shot algorithm. YOLO stands for you only live once. It has been well documented and well used in object recognition tasks in underwater environments, as well as specifically for autonomous vehicles. So why YOLO? YOLO is one of the, it's a single shot detection algorithm. First of all, it goes for a single pass to detect the bounding boxes as well as the probability of those. And it's like a real-time deployable model even on low parameter, even on low configuration hardwares. So this is the structure of the YOLO architecture. I won't be going in depth about this architecture, but what we can say is we have a backbone network, a feature pyramid network ahead, and eventually the loss calculation. So the backbone model is splitting it's a decoder model basically, and it's splitting the input image into multiple layers. And then we have the feature pyramid, which is concatenating it and passing it through the head to eventually calculate the losses and generate the output boxes. So this is the output screen of the YOLO model, which we have trained. As you can see, this is the bounding boxes that are being detected by the YOLO model, and this is the object class. That's 0 for the concrete cracks. So that's another screenshot, and I'll just move to the conclusions and results. So the proposed algorithm which we have proposed allows the ROV to follow a predetermined path which has been laid by a worker in the Stilling Basin, that is the yellow rope, and it's able to generate a trajectory as well as operate at an effective rate of more than 15 FPS. So I'll come to the sway error graph. So what these graphs are, first of all. So what the experimentation we did was we left the ROV on a curved path at a distance from the rope. So the ROV eventually was able to center itself across the rope and also reduce the error. So this is the sway error. As you can see, this is some disturbance that was observed. The ROV first moves towards, it moves towards the rope, and then it's eventually able to move its error towards 0. It's in fact less than 0.03 at most of the intervals. Coming to the yaw error, since in the condition that we tested for this following graph, the yaw was not changing much, so it remains near to the 0 value. It was almost -3 for this scenario. So for the task of concrete detection, pre-trained weights were used on YOLO V7, and then we did a test and split, and these were the losses obtained. We had a train box loss of 0.01238, which is a good value to deploy it on field. So I'll just play the video here. Yeah, so this is the ROV in a small, you can see a bucket kind of a structure. And what we're doing is basically we have run the algorithm and we have stopped the surge value. So when I displace it from the rope either towards the left or the right, The ROV is able to correct its yaw angle first and the sway angle first, sway then to center itself. It's as you can see in the picture, it's segmenting not properly because there was a weight kept to lower down the rope, so that's not being segmented. But the rest of all, it's able to correct itself. Yeah. I'll also come to the simulation. Yeah. So this is a representation of the simulation in the gazebo simulator. So the ROV is left from a distance and it's eventually able to detect the rope, and then it's able to center itself across the rope to follow the path. So the detection of concrete cracks can be done both on board in real time, or apart from that, if we want, we can collect the data for later time and then do the image enhancement, and then also we can do the calculations. So these are the references that I used for my work, and I'll also like to acknowledge Pramod sir for his guidance and NIO for their guidance across this project. It would have been possible without them. Thank you.